Look around at the range of human skin tones on this planet, every shade from the deepest brown to the palest ivory, scattered across every continent, every city street, every crowded market, every family photograph. And then consider this, every single person alive today ultimately descends from early human ancestors in Africa who had dark, melanin-rich skin. So what happened? It's a question people rarely stop to actually ask, because skin color feels so permanent, so obviously tied to where someone's family comes from, that it's easy to forget it was ever anything other than what it is right now. But rewind far enough, past every migration, every border, every culture we now associate with a particular look, and the story collapses down to one single starting point, one shared ancestor, one shared shade of skin. The answer isn't really about color at all. It's about something happening invisibly, underneath the skin, a quiet biological negotiation that's been running for millions of years, long before anyone had a word for any of it. Deep inside your skin sits a pigment called melanin, and for most of us, we barely think about it beyond a sunburn or a suntan. But melanin isn't decoration. It's a survival tool, doing two competing jobs at the exact same time, a constant balancing act happening quietly in every cell, every single day. It acts as a natural sunscreen, shielding essential molecules like folate and DNA from the damage of ultraviolet radiation, while still letting through just enough UV light to trigger the body's production of vitamin D. Too much protection, and the body can't make enough vitamin D, too little, and folate and DNA start breaking down. Melanin's entire job is holding that balance, tuned precisely to whatever amount of sunlight a body happens to be living under, near the equator, under the intense, unfiltered sun of East Africa. That balance worked perfectly. Homo sapiens evolved there with dark, melanin-rich skin, hair, and eyes, a direct shield against some of the strongest ultraviolet radiation found anywhere on Earth, sunlight strong enough, day after day, generation after generation, to make that protection essential rather than optional. It wasn't just sufficient. It was ideal, precisely tuned to the environment that shaped it, a fit so exact it would take an enormous change in circumstances to ever disrupt it. So what happened when humans started walking away from it, generation after generation, further from the equator than their bodies had ever been designed to go? As early humans began migrating out of Africa, spreading gradually toward regions with dramatically less sunlight, walking further north each generation, into landscapes their bodies had never been shaped for, the very trait that had once protected them so effectively became something else entirely, a liability. Two major dispersal events mark this shift clearly. Homo erectus moved into Eurasia roughly 1.8 million years ago, and much later, Homo sapiens followed a similar path outward from Africa around 55,000 years ago. Both groups carried the same dark, sun-adapted skin into environments where sunlight simply wasn't as intense or as constant. Picture it. Skies grayer, days shorter, sunlight filtering weakly through clouds and long winters, nothing like the direct equatorial glare their bodies had evolved to withstand, whole seasons passing with barely enough UV reaching the skin to matter. Suddenly, that same protective melanin, once essential, was blocking far more UV light than these bodies actually needed to survive. The body couldn't simply choose a new skin color. So how does evolution solve a problem like that over thousands of generations? This is where the leading scientific explanation comes in, known as the vitamin D, folate hypothesis. It's important to frame this clearly. This is the leading theory among researchers, not an absolute, settled fact, and researchers themselves are careful to describe it that way. According to this model, dark skin does an excellent job protecting folate, a nutrient critical for healthy cell division and development, but in low UV environments, that same protection blocks too much sunlight to produce adequate vitamin D. Lighter skin flips that trade-off, letting in more UV to support vitamin D production, at some cost of folate protection. As natural selection favored continued vitamin D production in these lower UV regions, populations gradually lost some of their constitutive pigmentation, generation folding into generation, the change so slow no single lifetime could ever have noticed it happening. Vitamin D itself isn't a minor detail either, it plays a genuinely vital role in bone strength, immune function, and even reducing risk for certain cancers and heart disease, health consequences that stretch across an entire lifetime, meaning this trade-off carried real, lasting consequences for survival, not just for one generation, but for every generation that followed. For most of the 20th century, scientists thought they already knew the answer to why skin color varies at all, confident enough to teach it as settled fact in classrooms for generations. And they were wrong. For decades, a different, Once popular theory dominated the conversation, the idea that melanin evolved primarily to prevent sunburn and skin cancer. It made intuitive sense on the surface, an easy story to tell, an easy one to believe, but modern research has directly challenged this explanation. Sunburn and skin cancer, it turns out, have negligible effects on reproductive success, meaning they occur too late in life, generally after reproductive years, to meaningfully shape natural selection. An idea that once seemed obvious simply doesn't hold up under closer scientific scrutiny. If it wasn't sunburn or cancer, something even stranger was happening at the genetic level, something that had nothing to do with disease at all, and remarkably, it happened more than once. Lighter skin didn't evolve just one single time in human history. Genetic research has verified at least 3 separate, independent occurrences of skin depigmentation evolving across entirely different hominin lineages, each one arising separately as different populations dispersed into their own low UV environments, thousands of kilometers apart, with no contact, no shared knowledge, no way of knowing another population was solving the exact same problem at the exact same time. Different genes, different populations, different points on the globe, and yet, evolution kept arriving at strikingly similar solutions, again and again, almost as if the same problem, presented with the same basic biological pressures, simply had a limited number of workable answers, and nature kept rediscovering them independently. Scientists increasingly describe human skin pigmentation not as fixed categories at all, but as existing along a continuous spectrum, a kind of sepia rainbow, shaped repeatedly by migration, local sunlight conditions, and the body's ongoing need for vitamin D. If evolution kept arriving at the same solution on its own, why does Europe's story turn out to be more complicated than sunlight alone? Here's a detail that genuinely surprises most people. To be clear, this next part applies specifically to Europe, not to human populations generally. Genetic evidence shows that lighter skin tones in Europe developed far more recently than most assume, as recently as around 5,000 years ago, a blink of an eye compared to the million-year timescales we've been talking about so far. And crucially, this shift wasn't driven primarily by gradual adaptation to local sunlight at all. It was driven substantially by migration, specifically, populations moving in from western Anatolia and the Russian steppe, carrying lighter pigmentation into the region and mixing with existing populations already living there. That means for thousands of years, early Europeans looked nothing like what most people picture today when they imagine ancient European ancestry, dark-skinned hunter-gatherers living across a landscape now associated almost entirely with pale skin. So what was actually driving this transformation? Was it sunlight? Migration? Or something far more layered than a single clean explanation? The honest answer researchers point to is complexity itself. Modern science increasingly treats skin color not as the product of one single clean cause, but as the outcome of several interacting pressures working together, layered on top of each other across thousands of generations, each factor pulling in its own direction, none of them acting entirely alone. Geographic UV exposure certainly matters. But so do specific pigmentation genes, diet-related genes affecting nutrient absorption, and even cultural practices, clothing, shelter, time spent outdoors, that shape how much sunlight a population's skin actually experiences day to day. Skin color, seen through this lens, isn't a simple equation with one variable. It's the layered result of genetics, geography, nutrition, and human movement, all interacting across thousands of generations, no single thread telling the whole story on its own, no simple formula anyone could reduce it to. All of this raises one final question, the same question hiding underneath everything we've covered so far. If skin color really is just the body's response to sunlight and geography, what does that actually say about the differences we see today? Bring it all together, and the full picture becomes remarkably clear. One shared origin in East Africa, where dark skin first evolved as protection against intense equatorial UV radiation, under a sun that gave early humans no other option. Repeated, independent adaptations as separate populations migrated into lower UV environments across the globe, arriving at the same answer without ever knowing it, without ever comparing notes, separated by oceans and continents in thousands of years. And later, entirely additional layers, like the migration-driven lightnings seen in Europe roughly 5,000 years ago, reshaping the picture even further, proof that this story never really stopped unfolding, and likely never will. Every skin tone on Earth today is really just a different chapter of the same 5 million-year-old story, written by sunlight, migration, and the human body's constant effort to find balance wherever it happened to end up. Every difference we see today began with the same ancestors under the same African sun. We didn't become different kinds of people. We simply adapted to different worlds.